Okay.
There is this, but
I have
the
this.
mic
Yeah,
already. Okay.
I have the mic.
It's better that we switch this.
Yeah. So good afternoon, everyone. Thanks for being here, especially thanks to members of the committee, and welcome to this defense. So without further ado, let's start with the presentation. So first of all, motivation. Why did I do what I did? First of all, we know that field theories, and in particular QCD, that's the focus of our studies, change drastically their behavior, changing the energy scales, because it faces phase transitions. What does it mean? That the coupling turns from weak to strong, or vice versa. The relevant degrees of freedom change completely, and also the realization of the fundamental symmetries of the theory changes. So we are facing strongly non-perturbative phenomena. And we need a method that can tackle these. And a possibility is to use the functional renormalization group. Why do we use the functional renormalization group? Because as we said, it's non-perturbative, of course. And of course, the functional renormalization group allows to take nicely into account the fact that fluctuations are not all at once taken, but just by momentum shells. So you can link different degrees of freedom at different scales. And in principle, these all look nice, but there are, of course, limitations, because when you apply to full QCD, then the solution is very hard. And what can you do? You can use effective models. In this context, effective model shines. And then you may ask, why would you use effective models? As I said, because of course you have, the main reason is because you can actually do calculations. So you get simple calculations. And of course you can, you expect at least to capture the essential degrees of freedom and essential features of the underlying theory. But on the other end, you are sure that you're not capturing the full theory, because you're just focusing on some degrees of freedom, some regime of energies, and so on and so forth. So for sure you're losing some information. In particular, we are focusing on the chiral symmetry gradient and chiral symmetry of QCD. So we focus on two models. One is the ON model, and the other one is the Quark-Meson model. I present two results on these two models. So first of all, a brief introduction on functional renormalization group. As I said, it implements the idea of Wilson to integrate momentum scale by shell, by integrating fluctuation by momentum shells. And this can be done using the so-called effective average action, gamma k. Gamma k is basically the generator of the one particle irreducible vertices, and it flows, it depends on a scale parameter k, and it flows from the bare action at the scale lambda, which is the cutoff of your theory, to the full effective action in the IR when k goes to 0. And this is done integrating momentum shells of order k, so around k. And how do you construct this effective action? You start regularizing your partition function, so this z. You introduce the Schwinger functional, which is this w, which is there at the exponent. And this regulator that appears there, it's made such that it screens IR modes. And screening IR modes is done basically introducing a mass term, which is this delta S-like term. And then once you do this, you simply consider a Legendre transformation and you introduce your effective average action. Now, notice that in principle, if you just consider the effective average action as a full Legendre transform, this would be convex. But since you introduce this delta S there, this convexity is not guaranteed anymore. It's only recovered in the limit k to 0 when the regulator vanishes. Why do I say so? Because of course the regulator has to fulfill some properties. And the first one, as I said, it has to implement IR regularization. And this IR regularization is implemented by the fact that it goes as a, let's say, as k squared, so as a constant bigger than 0 when p squared over k squared goes to 0, so for small momenta. Now, of course, we said we have to recover the full effective action when k goes to 0, so the regulator has to vanish in this limit. And then the third condition is that we have to recover the bare action in the limit for the cutoff k to lambda to infinity. And this practically is not possible usually, but it's sufficient to send the cutoff to a bigger value, a value which is bigger than all the scales involved in your problem. So once we have all of this, we're ready to face the equation which describes how fluctuations are taken into account by lowering k or t. T is this variable we define there depending on the scale k, and is useful for our later purposes because it looks like a time, right? It goes from 0 to infinity. And now the features of the vectoric equation. We see it's a pretty complicated equation because it's a functional integral differential equation. And from the presence of the regulator in two places, so dtrk and rk in the denominator, you see that the purpose is twofold. So we said the IR regularization before, and also usually dtr is peaked around the momentum shell of order k squared, so p squared over k squared. So this means that implements the idea of integrating in momentum shells. A key feature, fundamental feature, is that for the properties we highlighted before, you are expected that the effective average action and the trajectory that it falls in the so-called theory space, so the space spanned by all the possible operators compatible with the symmetry, this trajectory depends on R, but the final point does not. So this is ensured by the regulator, but we'll see how we tackle this. And then the structure is very nice because in principle it's an exact loop structure, but it's very complicated to solve. So usually you have to rely on ansatz. And in particular, we use the so-called derivative expansion, which means that you expand your gamma k in terms of increasing power in the derivatives. So you have an effective potential, you have a wave function normalization factor, and so on and so forth. We will focus on the LPA. LPA means that the only scale-dependent term is the effective potential. Now we can move to the first model, the ON model. This is a pretty simple model, so one may ask, why are you studying this? So first of all, we have a collection of n scalar fields, pretty simple, kinetic term, potential term, which depends on the invariant of the theory, which is just this scalar product of the fields. And we have a potential, which is quarting in the fields. Now, the interesting feature is that this simple model exhibits a spontaneous symmetry breaking. You go from the ON symmetry down to ON minus 1. And this symmetry is recovered at sufficiently high temperature via second order phase transition. And here you can see why we're studying this. First of all, because of universality, because it's a simple model, okay, but we know that close to phase transition, the relevant details are not the UV details, but the infrared one. So the symmetries of the symmetry of the theory or the dimensionality. So for example, this very simple theory can take into account the chiral symmetry breaking into flavor for QCD. And of course, it's very easy to solve. So you can use it as a framework to test numerical methods, to extract, for example, of something we did, to extract errors on the critical exponents and so on and so forth. So it's very useful and very adaptable for your purposes. So first of all, we show the flow equation obtained in the LPA. And the first thing we can notice is that it actually does not depend on the effective potential itself. So this is a very important point, because since it doesn't depend on the effective potential itself, it seems natural to define a variable which is just the derivative with respect to sigma of the effective potential. And this is this small u that we have there. And in this way, we can, if we take the whole derivative of the flow equation with respect to sigma, we end up with a very nice equation, which is exactly an advection diffusion equation. And this advection diffusion equation, we can see there as two contributions that we are labeling, we are explaining why we're labeling them like this. We're labeling as advection and diffusion fluxes. So why are we calling them like this? Now we go to basically to the so-called primitive form of the PDE. So we take the sigma, the sigma derivative, and we see that we have exactly this U prime structure and this DUF. So this is exactly an advection equation. Of course, there is this explicit dependence of F on sigma, but this is a source term, let's say a U-dependent source term, because it's not oriented, so it's not important for our discussion. So we see that this advection coefficient, if we analyze it, we see that it is always smaller than 0. So this indicates towards where the conserved quantity is transported. So this means that if we have a finite minimum, this advection coefficient always tends to restore the symmetry, because it always goes towards smaller values of sigma. So if we instead look at the diffusion part, this is important that, okay, we also explicitate the second derivative of U, so we see this diffusion structure. And it's very important for stability that this coefficient is bigger than 0, because if you add a negative coefficient, this would mean that the solution would be concentrated, and so this would explode. So because diffusion tends to smear. And this we're going to solve this using a finite method, a finite volume method, which is the Gargan retardant. We're not going to talk about this, but it's a very nice method. So now we look at some results for the effective potential. We see how the effective potential, this is the derivative of the effective potential, how the derivative of the effective potential changes as we increase time. So already this is a t equal 1, and these are different curves obtained, different potential obtained for different values of the minimum in the UV. So we see that the bigger the minimum is, the more broken the symmetry is. And if we go then to higher time, we said that we should recover convexity. And at the same time, we also have a finite minimum. And these two things clash into a plateau. And that's what we see there for the very broken phase. And the same thing we can see for the effective potential. We integrate, and that's the effective potential. We see the very same thing. Now we go to the critical behavior. In the critical behavior, we can see that since we are close to criticality, it's a very useful theorem. We can use the dimensional reduction phenomenon. So instead of using finite temperature, we can just use d equals 3 and t equals 0 flow equation. This is very useful. And so, but now we have to identify which parameter plays the role of temperature. In this case, it's clear that it's the minimum of the potential in the UV. The order parameter is, of course, the minimum of the potential in the IR, because if it's 0, you're in the broken phase. If it's different from 0, you are in the so if it's 0, you're in the symmetric phase. If it's different from 0, you are in the broken phase. But what does play the role of the relevant parameters role? Because if you are, if you have a value which is bigger than, let's say, a critical value, then you end up in the broken phase. If it's smaller, then you end up in the symmetric phase. And this corresponds in temperature to smaller critical temperature or bigger than the big critical temperature. Now we are facing a second order phase transition. So we are looking for a scale independent solution of the flow equation. And to do so, we just, as we said, the relevant parameter is rho 0. So we just take the quartic coupling into a fixed value, and we tune this value of rho 0. And what we expect, since we said that we rescale it, because of course, only rescale quantity will exhibit the scaling behavior, the scale independent behavior. So if we end up in the broken phase, so for a value which in the UV is bigger than the critical value, then this means that our rescaled value, our rescaled minimum will diverge, because it will go to a finite value and then divided by k will diverge. Otherwise, if we consider a symmetric phase, then the minimum will go to 0 at a finite k, and then when you divide by k, it's still 0. So this is exactly what we see here. So we see what we expect as a scaling solution, and then we see that curves that deviate upwards are the one for rho bigger than rho critical, and the one which go down are the one which lead to the symmetric phase, and the one associated to a lower value with respect to the critical value. And from this now we can extract critical exponents. It's pretty simple, pretty straightforward, because we just take what there would be a correlation length as a function of temperature. Now it's a function of rho, and it's just t minus tc to the power of minus nu. Now it's rho minus rho c to the power of minus nu. And now we connect, of course, the mass to the inverse of correlation length. So we calculate the mass as the second derivative of the potential. And then you just take this relation as the previous one, you plug them together, you take the log, and then you have basically a linear relation, and the slope is given by 2 nu. So you can extract 2 nu by this very simple formula. And that's exactly what we did here. So just a point here, you see, okay, we take the slope, but there are some points which are a bit off. At the beginning, let's say, and at the end. At the end, it's pretty understandable because we are getting far away from the scaling regime. So these points just do not follow the scaling laws. On the other side, you may say, okay, but I'm very close to the critical value. Why am I deviating? Because actually, this value is not the exact one. So we are, let's say, when we extract this value, we go always in between the two values, broken and symmetric phase. So we have an approximation of this. So the closer you get to this approximate value, the more you have an error. And that's what you're seeing there. The same thing you can see for the critical exponent beta, you just the order parameter, which is 0 in the symmetric phase and goes as t minus tc here, rho minus rho 0 to the power of beta. So again, you take the log of this relation and you end up with a straight line with slope beta. And that's what we see here, and that's exactly what we obtain. So again, we see those points which deviate as we argued before. And this is the, let's say, sum up of all the results for the various critical exponents, which beta and nu, they are the two we calculated, for various values of n. And the feature I want to highlight in this plot is that they nicely, let's say nicely, tend to converge to the value for n to infinity. And in this case, because of course, in the n to infinity, the LPA becomes exact. So you expect to recover the fact that you actually get the critical exponent you expect to a larger limit. And this is more or less the trend you're seeing here. So now we change model. We go to the Quark-Mason model. And the Quark-Mason model, it still implements in some way the ON symmetry, but this time you also have quarks. So you have quarks coupled to mesons via Yukawa coupling. And in this case, you can implement chiral symmetry breaking, and this becomes a spontaneous symmetry breaking of the O4 symmetry down to O3 symmetry. And which plays the role of the order parameter, so the chiral condensate. In this case, is the expectation value of the sigma field. So it's 0 when the symmetry is restored, and it's greater than 0 when the symmetry is broken. And here we're working at food temperature. So this is also, again, a well-known model. So we already know what we can expect from the phase diagram, which is in the mu equals 0 direction, we should get a second order phase transition in the chiral limit. Then we have a first order phase transition in the mu direction at t equals 0. And then the two lines meet at a critical point. And again, we are using the LPA ansatz to study it in the FRG framework. Now we move to the flow equation. In the flow equation, again, you have to choose the regulators. So I just highlighted these two regulators just to show you the appearance of these regulator shape functions which are there, which should then appear in the energies of the particles. And we can see that we already took the derivative. We already substituted the sigma field. We already substituted the derivative. And here we have the very same equation we had for the ON model. So we have, again, diffusion advection equation, but with an extra term. This extra term is the source term. The source term is like this because it doesn't depend on the U variable. So it's a pure source term, which creates the minimum or just eliminates the minimum. So it's directional. And again, we see the nice property we expect from the diffusion and advection. So the advection, again, brings the solution, so restore the symmetry, brings the solution to smaller values. And the diffusion, again, it's bigger than 0, the coefficient, so it smears and doesn't concentrate. So what are the results we expect for the phase diagram? That's exactly what we get here. Well, most of. Because on the left side, we have the mean field study, which we're going to define soon, but basically is without considering the feedback of the bosonic fluctuation in the flow equation. And this is exactly the phase diagram we expect. So second order, first order, and critical point. Then in the FRG case, it looks a bit weird. I'm not going to comment too much on this, but you see this weird triangular region where there is another phase transition. And this is related to some issues that maybe we can discuss. So this is the result we obtain in the functional normalization group method. Now we move to another, let's say, chapter of this study, so the regulator dependence. Because how stable are these results under the change of the regulator, one may ask. Well, we said before, and this was a point I highlighted before, that in principle you should have 0 regulator dependence if you have the full flow equation, but you don't, because at some point you truncate. So first of all, there are artifacts from the cutoff. How do you get rid of this? You use the so-called RG consistency, which means that you enforce the fact that the IR effective action is completely independent on the cutoff. And this usually, most of the time, is done by tuning the parameters in the UV, so in the initial condition. But once you do this, still, you are not guaranteed anymore if you truncate your flow equation to obtain unique IR results. And this is due to the fact that, as I said before, you're basically truncating the theory space. So you're not even sure that your IR minimum is there anymore. So in principle, nothing is guaranteed. So you need to define a stable procedure to compare the different results. And this procedure is basically fixing some IR observables in the vacuum, like the position of the minimum and the mass of the, so the curvature mass. And then once you have fixed this, you're sure that all the differences you observe when you go to finite temperature and finite chemical potential are both cutoff and regulator artifacts. So you can basically quantify these effects. So first of all, we start with the mean field. As I said, in the mean field, we have no feedback of the bosons into the vectoric equation, which corresponds formally to a large NC limit. So the flow equation that we get in this case is pretty simple. It's very nice because it's just a source term. So it's just a source term. It means that you can do whatever you want with this. You can integrate, you can go up, you can go down in time. It's pretty simple. And in this case, indeed, we come up with a very simple strategy to ensure RG consistency and for the initial condition. And this is the following depicted in the picture there. So you start from a cutoff lambda, then you go down to the vacuum with a given regulator. And once you have this result, then you can flow up again with a given, with the same regulator, let's say lambda prime, and you get to a cutoff lambda prime, much higher than lambda. And the nice thing is that if in the way you construct this, all the initial condition you produced in this way flowing up are by construction RG consistent, because then you flow down and you get to the same vacuum. So this is by construction RG consistent initial condition. And using this procedure and fixing a sufficiently large cutoff, you see that exactly all the regulator shape functions we choose collapse into a single phase diagram. And this is a very nice result, but of course, this is just the tip of the iceberg because we expect this. This is a well-known property of the mean field phase diagram, which is independent of the regulator. So this is just a test. Now we move to the real deal, which is the LPA. And the LPA, this is not possible anymore because you have now diffusion terms, so you cannot flow upwards. So you're losing this property. How can you do? As we said at the beginning, so you fix the value of the IR mass and the position of the minimum, and then you match the vacuum for the different regulators. But is it really possible? Then you need to study actually the so-called parameter space. So you start with your quartic potential in the UV at different cutoffs, and then you see how these parameters can be chosen in order to fix the IR values. And in particular, on the left, you see that these are the two parameters, and all these lines contain, for different regulators and different cutoffs, all these lines contain the same IR minimum. So the same IR minimum is there. So you see that basically, as you increase cutoff, these, of course, you have limitations on the parameter space. For example, trivially, you have that lambda has to be smaller than 0. So you cannot start with a negative lambda. And then you have also a constraint from the flow equation. So you also have a lower bound on lambda. And then you can see that actually it seems that this parameter space gets larger and larger. So it seems that you can sample more and more in the UV space, getting the same results. But how does this reflect into the IR? Actually, the other way around, because the larger is your parameter space, so the larger is your cutoff, the smaller is the accessible mass. So all these bands that you see on the right plot are all infrared mass obtained with the same IR minimum, but for different cutoffs and different regulator combinations. So you see that this actually shrink almost to a point when lambda becomes very, very large. So it seems like you have a prediction of the model for this curvature mass if you fix the minimum. And now actually the comparison becomes a bit tricky because you see that the bands do not, if you choose a large enough cutoff, then you can see that the bands overlap. But if you start squeezing them, actually they start not to matching. So you have to be careful. But for our purposes, it's sufficient to choose them such that they almost overlap. So they're very close. And we're going to see soon why. And in particular, as I said, this band structure, if we move to the phase diagram, so upward and lower bound, appears also in the phase diagram. So on the left, we're using the same regulator, but just for different cutoffs. And you see that as the m squared, or as the curvature mass, also the phase diagram tends to collapse into a single phase diagram. This means that basically you are getting rid of the dependence of the cutoff. So you get lambda independent, so large lambda independent phase diagram. So you have a phase diagram independent of the cutoff. And it's very interesting. And then on the other side, you see that if you compare different regulators, also the different regulators tend to collapse into a single curve. And this is also completely not expected from what we said before. So this is a very interesting feature that you can remove regulator and cutoff dependence is just increasing the cutoff sufficiently large. And another thing I want to highlight on coming back to the left plot is that actually in this case, you see that, for example, if you stick to 1 GV cutoff, you have a very large band. So usually people in literature say, okay, let's fix a cutoff lambda equal 1 GV, and then we fix the minimum. But if you don't fix also the curvature mass, or at least just fixing the minimum, you can obtain almost whatever result you want, because you see the phase diagram is very large. The bands are huge, depending on the cutoff. So you need to choose a lambda which is sufficiently large. So we can wrap up what we said up to now. So we are using the FRG to study QFT. In particular, we describe the Wetterich equation, and then we apply this approach to the ON model. And in particular, we extracted this very nice hydrodynamic approach to FRG, and we study the critical behavior of the ON model and the critical exponents. Then we applied the same method to study of the quark meson model and to the phase diagram. And in principle, also we investigated the truncations and the regulator dependence in the quark meson model. And the main point is that we were able to find a systematic approach to remove the cutoff dependence and to remove the regulator dependence. And so that's what we expect in the mean field, so completely trivial. So okay, good check. But as we said in the LPA, it's completely non-trivial, and this is very interesting that we were able to just fixing the cutoff to fix these two parameters, so remove UV cutoff and UV initial condition dependencies. So what's next? We can basically redo what we did at higher truncations. For example, we can extend the hydrodynamic formulation to beyond LPA. This would be very interesting, for example, for the ON model, because we studied, one of the results we studied in the thesis was the errors on the critical exponents. But one of the errors we didn't investigate was actually the truncation error. So what happens when we increase the truncation? What happens in that case? And this is something we can do. Something else we can do is replicate this systematic approach to the quark meson model. So for example, let's see also in this case how these regulator dependence and the truncation dependence comes into play when you improve the truncation. And also, of course, you can incorporate different degrees of freedom, change theory, include indeed, for example, dye quarks and stuff like this. So change completely your framework and repeat all these studies. Thanks for your attention.